Hey guys, today we're going to do some of the application problems that come with exponential growth and decay. So our question today is, how do I apply logarithms to real-world situations? Okay, the first thing that you need to know is this formula. The formula y sub t equals y sub 0 times e to the rt. And so what each of those pieces means, y sub t, that's going to be your amount after a given time. And I realize now that I made this nicer so that way we don't have to try to read my horrible handwriting. Okay, amount after time. So y sub t, if they say this is the amount after 2 hours, that would be that amount. Okay, your y sub naught, that's your initial amount. So whatever you start with, that's the beginning. It's y naught, y sub 0, whatever you want to think about that. But that's your initial amount that you started with. Your r is a rate. And the important thing about your rate is that it needs to be written as a decimal. And for your rate, it's okay if it's negative. If it's negative, that just means it's decaying or it's getting less, whereas a positive rate would tell you that it's getting more and it's growing. Okay, and then t is time. The big thing about time is you need to stay consistent. So if your problem talks about minutes, you have to make sure your answer is in minutes. If it's hours or months or days, whatever it is, you just have to make sure that it's consistent throughout your problem. Okay, there are a bunch of uses for this, and you may have seen some in your physics or chemistry classes. The half-life formula for radioactive decay, for interest when you're compounding and finding money in your bank account continuously, you're going to use a different formula than in times per year. That's just saying I'm going to compound it every month or something like that. And then finally, population growth, that usually models that exponential growth thing. So let's do an example problem. Okay, again, these are all of the important things you need to know as we're solving this problem. So the half-life of an isotope of carbon-14 is 5,730 years. This is carbon dating. An organic sample has 30% of carbon-14 remaining. How old is this sample? Okay, these are the steps that we're going to do. So the first thing I'm going to have to do always, always, always is if they don't give you the rate, you're going to have to find the rate. And that is the most important thing. On any different types of these problems, you're going to have to find a rate. So in order to find that rate, I have to use what's given to me. The hard part about these is this half-life is not actually like that's how long the whole thing goes. It's just saying this is how long it takes for half of the sample to disappear. So if we start this, the easiest way to take half of something is to take something that's even, like 2. So let's pretend that I started with 2 grams or whatever units of my carbon-14, and I want to know how long it's going to take for that half-life, that rate that we're looking for. So I'm going to say my new thing, amount after time, would be 1. That's half of the amount. Then I times this times e, and then we don't know my r, I have to solve for that, and then the time. So again, the half-life is actually the t in this equation, the time. So I'm going to go ahead and try to isolate e at this point. So I need to get e by itself so that way I can actually solve this problem. So I'm going to go ahead and divide both sides by 2. And so I'd have 0.5, or 1/2, is equal to e to the 5,730 r. Okay, now I'm going to rewrite this as a natural log because I know that's how I get rid of my e, my base e. So I'd have natural log of 0.5 is equal to that exponent. And so now this is just a point of using my calculator. So I can take that natural log of 0.5 and divide it by that coefficient of r, and that will get me my answer. So your natural log button's right here, 0.5, divide by 5,730. And so we would find that my rate is really, really small, but that makes sense. So my rate would be negative 1.2 times 10 to the 4. So there's technically 3 zeros in front. So it's negative, it's decay, that makes sense. So I'd put 3 zeros in front of that number. Be careful where you round here because where you round does change the amount of the problem. I like to use the actual value from my calculator when I continue with my calculations. Okay, so after this point, we now have a real equation. I can rewrite this equation with this new rate. So plug in this r, and then I can find what they're actually asking me. So they want to know how old is the sample. I'm looking for a t. So I know that I have 30% remaining. So the easiest way that I could find 30% is if I had a sample that was 100, and if I take 30% of 100, that's 30. Then I have e to the, we know that my r is this value, and again, I'm going to use that value from my calculator, but I'm going to write down what I kind of used right here, and then I don't know how long it's going to take. Now it's going to be the same steps that I just did. I need to get e by itself. I don't know why I'm trying to divide by 30 here. So I'm going to have 0.3, and then I know that I need to take the natural log of that in order to get rid of this e. I lost a 0. Okay, and so I'm going to take the natural log of 0.3, divide it by that big number. Well, I guess it's a really small number. It just has a lot of numbers in it, and that should give me my time. So again, I'm going to take the natural log of 3, then, natural log of 0.3. I don't know what I'm doing here. Oh, calculator, come on. And then I'm going to divide it by, and again, you can just go paste this number that's up here. And I would find out that this sample was about 9,953 years old. And that's all you got to do for these. So again, tomorrow you're going to see a lot of different types of examples of this growth and decay, but you just need to know this one formula, and you can do any of those types of problems. See ya!